Hi again, everybody, and welcome to Networks 101. This is a short video aimed at an introduction to networks in Year 11 in VCE in Melbourne, Australia. But you're welcome to join in if you are interested. So, 101, how to take a walk along a trail, then onto a path, round a circuit, and then cycle through it all again. Basically, that's all the terminology that you need to be au fait with when you're dealing with networks. Along with two down here, two friends, Euler, spelt Euler but pronounced Euler, and Hamilton. And we'll deal with them a little bit later on once we get the basics done. All right, straight into it. First up, a walk. Okay, that's just a sequence of edges that connects at least two different vertices on a graph. Okay, so here we have a graph. Now, or a network, you can call it either. Now, vertices. These are vertices. We have 5 vertices here, A, B, C, D, and E. These are joined by edges. Now, these are lines that go between the vertices. There are edges. So we've got 1, 2, 3, 4, 5, 6, 7 edges in this graph or in this network. Okay, a walk. So it's just a sequence of edges, just a random sequence of edges. Well, here's one walk, A to B, and we write it as A to B. Quite simple. Here's another walk. Let's go E to A. We're going to go a bit further. One between two vertices, not very far. Let's go to C as well. So we add the C. And let's go to E. Back where we started. Still not enough. All right, we want to go visit somebody at A. That's all called a walk. That whole thing is a walk. So this walk in red is E-A-C-E-A. Now, a few things to remember about this. 1, you can start anywhere on the network. You can finish anywhere on the network. You can repeat edges, as we did over here. You can repeat vertices. All right. Quite simple. A trail, a little bit more complicated. Actually, I will say this, don't worry. I'm going to disappear shortly once we've got these basic definitions out the way, and I'm going to put a screen up. You can just take a screenshot of that screen, and we'll have all the details of each of them. Let's get on to a trail. A walk with no repeated edges, so slightly different. So let's have a look. E to A, we did that before. A to C, we did that before. Go back down to E. Now, that's where we went before, wasn't it? Back to A. But hang on. This one is no repeated edges. A trail has no repeated edges. So we better take that one off. So we're stuck at E. Let's go the other way. See if we can go a bit further in the trail. Well, off to D. Yep, we can do that. Up to C. We can do that. Up to B. We can keep going. We can get to A after all that. No repeated edges. Okay, so that's EAC, EDCBA. Great. Rules. You can start anywhere, same deal. You can finish anywhere, same deal. You can repeat vertices. As you can see, we've done C a few times. We've finished up at A. We've done A a couple of times too. We've done E a couple of times. We started E and we went back there. Right. But you cannot repeat edges. Okay, that's the difference between a path and a trail. You can't repeat edges. Sorry, a walk and a trail, not a path. A walk and a trail. You cannot repeat edges. Now we do a path. I'm getting ahead of myself. Sorry about that. Similar to a trail, but this time that's no repeated vertices. Okay, so we can't do E twice or A twice. Let's have a look. We'll start back at E and go to A. Looks familiar? Okay. Then we go across to C. Great. Good so far. Haven't repeated any vertices. if we come back down that way, we can't come back down that way because we're repeating E. So we can't do that. Where could we go instead? Well, we'll try down to D. We haven't been to D before, so that's D. But now we're sort of stuck because the only place we can go back to is E. So that's as far as that path can take us. We could have gone up to B. We couldn't go back down to A because that would be back down to A at the vertex we've already been to. But this one, E, A, C, D, we're stuck there. Okay, so again, we can start anywhere. We can finish anywhere. We cannot repeat vertices. Now, the good news is if we can't repeat the vertices, by default, that means we're not going to be able to repeat any edges either. Okay, next one, a circuit. Okay, so that's a walk with no repeated edges that starts and ends at the same vertex. All right, so let's make a note of where we start. We'll start somewhere different. We'll start at D. Okay, D. Let's go up to C, up to B, to A, and across to C. We can go back to C because it doesn't say anything about vertices, does it? It doesn't say we can't repeat them. We'll go to E now, up to A. Hang on. Can we go any further? Hang on. This doesn't, we can't go any further than A, can we? But we have to go back to the same start vertex. So A is no good to us up there. So we've just turn it around and then we'll go across to D. All right, so D, C, B, A, C, E, D. All right, looking down below us, we can start anywhere, same thing. We can repeat vertices, we can't repeat edges, and we have to finish off back where we started. All right, got that one? Awesome. Next, a cycle. You heard all these names before, they're on the front slide. There's a few of them. Get them into your bound references. A walk, so a cycle is a walk with no repeated vertices and starts and ends at the same vertex. All right, let's go back to E. Got sick of D. E, up to A, across to C, back to E. What can we do there? No repeated vertices. Hang on. D, we've no repeated vertices. What are we doing? Hang on, where are we going? Starts and ends at the same vertex. We've gone too far, haven't we? Hang on, D, can't go to C. Can't even go to D. You're right, we have to stop at E because we start and end at the same vertex with no repeated vertices. Okay, so the rules for this one, can start anywhere, you can't repeat vertices, you must finish at your start vertex. All right, we won't repeat any edges on that one for the same reasons we couldn't do it before. If you can't repeat a vertex, you can't repeat an edge. Okay, I'm just going to move on to the next bit. And this is where you want to get your print screen or do your screenshot. It's just a summary of all those things so far. So I'm going to disappear so you don't get my beautiful face on your screenshot. Here it comes. All right. See, there's the 5 things: the walk, the trail, the path, the circuit, and the cycle. They're things we've covered. I'm just going to disappear for a moment and we'll see you in a few seconds. Go screenshots. And 3, 2, 1. Voila, I'm back. All right, let's have a look. A few more we got to get through. Connected graphs. They're pretty straightforward. There's a graph or connected network, if you want to call it that. You can see there are 6 vertices. There are edges connecting all the vertices. I can get from that vertex to that vertex if I need to. So obviously it's all connected. All right. This one has a special name though. This edge here. We've got two basic ones there, like we have down the bottom here. There's one set, there's the other set, and this one in the middle, oddly enough, is called a bridge. It's a bridge between the two parts. Down here, this one, obviously, no, that's not connected, is it? That's pretty obvious. Traversable graphs. Now, traversable, if you look it up in the dictionary, means you can get all the way around the graph or the network. So it has a trail that includes every edge, which basically, remember when you were in high school or even in primary school, you're in high school now, in primary school, you used to draw figures and used to have to try and trace the whole picture without lifting your pen. Well, that's sort of what we're doing here. So we have a trail that includes every edge, and you can get to every vertex without lifting your pen. Now, there's a few rules for this one. First, it must be connected, obviously. If it's not connected, we can't get across there. And you have two choices here. All the vertices must be of even degree, or exactly two vertices are of odd degree. What are the degrees of a vertex? Well, that's simply the number of edges that either go into a vertex or come out of a vertex. So this vertex here has degree of 2. So there's one that comes out there, one that comes out there. So degree of 2. This one, obviously, degree 2 as well. And third one, degree 2 as well. So this fits the criteria of all vertices must be even degree. Therefore, it's traversable. This one over here, let's go through all the vertices. So that's how we check. We go through all the vertices. That vertex has degree of 2. This one is degree 2. This one is degree 2. And this one is also degree 2. Great. The one down here, 1, 2, 3. So this one's degree 3. And this one, of course, you can see is degree 3 as well. Which criteria does that one fit? Well, it's this criteria here. Exactly 2 vertices are of odd degree. 1, 2 has to be exact. So this one is very much traversable. Third one down here, let's have a look. This vertex, what's the degree of this one? 1, 2, 3. Great, that's degree 3. This one, 1, 2, 3. That's degree 3. This one up here, degree 2. 1, 2, 3. That's degree 3. 1, 2, 3. Degree 3. Okay, so we've got 4 odd degree vertices. 1, 2, 3, 4. But this says exactly 2. That's no good to us, this one. This one is not traversable. You could, if you wanted, I'm going to do it briefly now, but if I could start here, there, 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 there. Did I just do that? 1, 2, 3, 4, 5, 6, 7. No, I've already been on that one before. No, I was right. Phew, scared me. No, it's not traversable. You include every edge without lifting your pen. Let's have a look at this one over here. Same thing, but the type of question you might be asked is to, okay, we have could we do to that network that makes it traversable? Pretty typical question. Well, obviously we only want 2 vertices that are odd degree. So we've got 2 down there. We could simply add a path between those 2, like that. Okay. Now that would change the degree of that one to 1, 2, 3, 4. And this one down here, 1, 2, 3, 4, that's degree 4. And all of a sudden it becomes traversable. You start down here and go 1, 2, 3, 4, 5, 6, 7, 8. Got all the way around it. Great. Now I'm going to give you a little tip. It's all to do with this without lifting your pen off the paper. Okay. The hint is, if you have a network that has 2 odd degree vertices in it, it's traversable, and you want to do it, you have to start at one of the odd degree vertices. You notice when I did it down here, I started here. If I started here, I wouldn't be able to get back to the start. Okay, always start down here at an odd degree vertex, or wherever there is an odd degree vertex. All right, traversable graphs. A couple more to go. Here we go. Euler Trails. Remember I mentioned Euler and Hamilton? We'll talk about Hamilton in a moment, but Euler Trails. Now, difference between a trail and an Euler trail is an Euler trail goes to every edge. A normal trail doesn't have to go to every edge, but an Euler trail does. So, way to remember, Hamilton or Euler. Euler starts with E, so does edge. Euler is to do with edges. Try and remember that one, Euler edge. All right. To have an Euler trail, but not a circuit, we have to fit this criteria. Exactly 2 vertices are of odd degree. That looks familiar, doesn't it? So we need to check if there's an Euler trail up here. Let's see, degree 2, degree 4, 1, 2, 3, 4, that's 4, 1, 2, 3 there, and 1, 2, 3 there. Beautiful. That meets that criteria. All right, let's pick a, remember what we said? Start at an odd degree vertex. I'm going to start at D. Start at odd degree vertex. I'm getting ahead of myself again. Let's start at D. And I think you know how to do this one. Let's go round the circuit. Sorry, round the network. And we end up covering everything. But did you see where we ended up? We ended up at E, not back at the start vertex. So that makes it a trail. So we ended up there. And how you'd write that, of course, is you write the Euler trail, begins at D, goes to B, A, B, E, C, D, E, and finishes. You've got every edge then. An Euler circuit, however, goes over every edge, which is the same, but then returns to the start vertex. So to have an Euler circuit, this one's slightly different. Not any odd degree vertices. All vertices must be even degree. All right, let's check this one. Degree 2, degree 4, degree, hang on, they're the odd degree ones down the bottom there, aren't they? How do we change that? That's right, we added an edge between D and E. There we go. That changes that to degree 4, and this one to degree 4 as well. Okay, pick a start vertex. We haven't got any odd ones we have to start at, so we can start anywhere. There's one, same spot, start at D again. Let's follow it around, see if you can keep up with this one. There we go, B, A, C, B, E, C, D, E, and back to D. Great. Whew. Wrote that one a bit quicker, this one. Sorry. Hope you could follow that. If you need to, you can always rewind it and go through it again. Last slide coming up, I promise. Euler's done. Let's go Hamilton. Now, difference between Euler and Hamilton. Now, Euler started with E, so Euler was edges. Hamilton is all about the vertices. I'm sorry, I haven't picked up a way to remember Hamilton and vertices. If you can think of one, please tell your teacher. I'm sure they're in the same boat. All right, there's good news and bad news about Hamilton. Hamiltonian paths go to every vertex in the graph. Okay, good news is, but you don't have to go over every edge. So if I started at A, I could just go to C, go to B, go to D. I've gone to every vertex. That's a Hamilton path, Hamiltonian path, A, C, B, D. Okay, doesn't matter about these 2 edges. A Hamiltonian cycle, same thing as before, every vertex, but then you return to the start vertex. Okay, but again, you don't have to go over every edge. Now, The bad news, I said there was good news. You don't have to go over every edge. The bad news is there's no real trick to check the degrees of the vertices or anything like that to see if it exists. It is purely trial and error. So I've given you an example down here. This is pretty obviously a zoo, a network of a zoo. All right, you come in the gate and little Johnny, your son, is desperate to go see the lions. Okay, so great, you go see the lions. But then you want to go to the hippos and then through the ostriches, which means you either have to go back to the gate and to the lions or through the lions again, off to the ostriches. But then you want to go to the eagles next, and so you have to go to the butterflies first, or it gets messy and you can end up walking for miles. The idea of a Hamiltonian cycle is that you can start at a vertex, get round as quickly as possible. This is one of the applications. Get round as quickly as possible in the minimum distance and see all of the animals. So poor little Johnny is not going to see the lions first. You can see that. He's going to see the hippos first, or he could see the eagles first. Let's have a look at one. There's a few of these, but let's have a look at one. So if we start at the gate, now, as I said, sorry, there's no rule about how to do it. So we just have to do trial and error. Let's see if this works. Gate to hippo, to lions, to ostriches, to butterflies, to eagles, and all the way back to the gate, all in one hit. One big cycle. All right, so this is one possible. This question, you could write the GHLOBEG, as I've done there. But because this is about a zoo, you're better off writing the cycle which goes gate, hippos, lions, ostriches, butterflies, eagles, and back to the gate. Oh, all right, that's a lot of talking from me. Now it's time to get some practice. Please, it's a lot to remember. All the trails, the paths, I can't even remember them all now, I'm brain dead. Euler and Hamilton, make sure you've got them in your reference book. Okay, that's the easiest way, and an example in your reference book. Okay, let's get into some exercises now. Get help from your teacher if you need it. Otherwise, enjoy starting your journey on networks.